Hey everybody, welcome back. I hope everybody enjoyed their long weekend. This is Mrs. Kroll. We are continuing our work on vectors, but we are going to be moving into some word problems this week. So, how can we apply the parallelogram law to find the resultant of 2 3/4 word problems? That's what we're going to be working on today. So the first thing we got to briefly go over is the parallelogram law, and actually we worked on it last week when we did some vector addition. We used the parallelogram law, we just didn't call it that. So real quickly what it says is the sum of the two vectors is equal to the diagonal of the parallelogram formed by those vectors. So if we have vector u and vector v and I wanted to add them together, well, we talked about taking vector u and the initial point of vector u is going to go at the end of vector v. Or I could take the initial point of vector v and put it at the terminal point of u. Either way, it creates this nice little parallelogram, and so the addition of those two vectors is always going to end up being the diagonal. Now, we always call that diagonal. We don't always call it the addition of them. Going back to last week, using some of those words, we're going to call this the resultant. And so my resultant is always going to be that diagonal. So we're going to continue using that property today, looking more at the pictures because we're going to have to write the component form later, so it's nice to always see the picture. So the next thing that we're going to look at is putting a vector in component form. I know we did that last week, and we always did it terminal minus initial. But now we're not going to always have terminal and initial points because we're going to be looking at things that are off the coordinate plane. So I have a vector that has a magnitude of 14 units and a direction angle of 65 degrees. I'm going to put it on the coordinate plane so that we can kind of see where the pieces are coming from. But then the way that I write it in component form is going to always hold true to all of these. So we don't always have to have them on that coordinate plane. So the first one I want to draw is, I know it's going to be in quadrant 1 because it's a direction angle of 65 degrees. So that's going to be 0 to 90. So I know that it's going to end up being somewhere in between there. Okay. So 65 degrees about to be right here. And it has a magnitude or a length of 14 units. So that length is 14 units, whatever it actually is. It doesn't really matter. But now when we write it in component form, what we use component form is to isolate my vertical component and my horizontal component. So how much is this moving horizontally? How much is this moving vertically to end up getting this vector right here? So I do know that this angle is 65. And it creates this nice little right triangle here because of the horizontal and the vertical components. So we can use some right triangle trig to help us out here. Right triangle trig is always your SOHCAHTOA. Okay. If I want to find out my horizontal component to go with the first part of my component form, if I was to actually find this side, I would be using cosine, because cosine was always your adjacent over your hypotenuse. So we'll use cosine here to help us, and then cosine will always go with our horizontal component, so we don't always have to look back at this picture. So if I'm going to write it in component form, it's going to end up being 14 cosine of my angle. I start with the 14 because that's my magnitude. Cosine is always going to go with a horizontal of 65 because that's the direction angle that I have. And then my vertical component, well, going back to that right triangle trig, opposite, that's always going to go with my sine because its sine is opposite over hypotenuse. So 14 sine of 65. So here's my vector in component form, 14 cosine 65 and 14 sine 65. Remember, cosine will always go along with the horizontal, and sine will always end up going along with the vertical. It's the way that it is because of the right triangle that's created in our right triangle trig. But you just need to remember which one goes along with which for horizontal and vertical. Now, I'm okay if you leave it like this, but we could also go ahead and plug it into the calculator and come up with a decimal approximation for it. So 14 cosine 65 is 5.92, and 14 sine 65 gives me 12.69. So I know I moved horizontally 5.92, and I moved vertically 12.69. This is actually going to be super important for us because this is how we're going to write out all of our vectors in the word problems. Okay, so let's flip to those then. This is the second page of your notes. There are 3 problems on here. We're going to take the time to do for sure the first one together. And then I'm going to tell you to pause the video and work on number 2, and then I'll come back over all of the answers for number 2. And then we'll do number 3 together. So it says the 2 trucks with a 37-degree angle between them pull on a stump. The truck's forces are 1,000 pounds and 1,250 pounds. Find the resultant force. Now, the resultant would just be that diagonal across, but since it wants the resultant force, that's always going to end up being the magnitude of that diagonal. I want to know what's the actual length of that diagonal so that I know how many pounds are pulling on this stump when both of those trucks pull at the same time. So here's my stump. Let's draw a picture, and I like to be as accurate as possible with these pictures, just because it helps with the parallelogram about where the direction angle should be, and then also it kind of makes sense with how many pounds it should be if you kind of have it drawn to scale. It does help out a little bit. So one truck is pulling at 1,000 pounds, and then there's a 37-degree angle in between them, and then the other one is going to be 1,250 pounds. So I'm just going to draw my first force right here, going straight across at 1,000 pounds. So if that distance is 1,000, I know my next distance needs to be a little bit longer than that to represent 1,250. And then there needs to be a 37-degree angle in between them. So about 37 degrees. And then a little bit longer, this one's going to be 1,250. So I'm going to go ahead and draw that parallelogram that we had before so I can see what the resultant vector would look like. I know that resultant vector is always the diagonal in this parallelogram. So this is my resultant, and its distance is going to be my resultant force. So what we want to do is this diagonal, I want to know that in its component form, how much is it moving horizontally and how much is it moving vertically. Well, since it's the diagonal, I know it's going to be the sum of these 2 forces together. So force 1 and force 2. Okay, I'm going to add those 2 together so that way then I can find out the component form of that diagonal or the resultant force. So let's write in component form, let's write the first force. So I know that it has a magnitude of 1,000, so I'm going to start there. And I know that I want to start with the horizontal component, so horizontal always goes along with cosine. But now I need an angle. Well, there's a 37-degree angle in between them, so one of them has to start at 0, which I'm going to start my 1,000 at 0 degrees, and then from that 0 degree, this one, 1,250 is going to be at 37 degrees. Okay, so cosine of my angle, which is 0, and then 1,000 sine of my angle, which is 0 again. Then force 2 is 1,250 cosine, because that's going to give me my horizontal of 37. And then my vertical component goes along with sine. Now, I want to find the addition of these 2 because that would give me my component form of that diagonal. So I know I can just go ahead and add down horizontally and then add down vertically. So I'm going to do some stuff on my calculator here. I am going to cover up my picture so that you can still kind of see my calculator and then see my work next to it as well. So the first one I'm going to add up is 1,000 cosine 0. And I'm going to add to that 1,250 cosine 37 to get a horizontal component of 1,998.29. Now, here's the thing though, I rounded it here to write it down, but we really don't want to round these answers at all. So the calculator does some nice things for us. It can store all of our answers, and it would store the entire thing. So that way I'm able to use the numbers even though you don't see them, they do continue off the screen. So it would store the entire thing. So if you go right above the on button, there's a button right here that has STO and a little arrow. That's going to store any of your answers. So if I want to store this, I would just hit alpha and then whatever letter you want. I'm just going to pick A. So this is going to be stored as alpha A. And then now anytime I hit alpha A, that answer will be recalled and it would be the whole decimal, so I don't have to worry about typing the whole thing in. All right, now let's go ahead and do my vertical component then. So my vertical component is actually going to be the same equation up at the top, except it's just going to be signs. So I'm going to take my calculator and I'm going to keep going until I highlight this equation that I want. And I'm going to hit enter and it will bring it back down here so I can manipulate it. And then I'm just going to go over and instead of all of the cosines, I'm going to hit sine instead and it will just swap them out nicely for me. And I can hit enter. And that one's going to be 752.27. Again, I don't want to use the rounded version. I want the whole thing. So I am going to store this one as alpha B. So now they're nice and stored in my calculator so that I still have them. But now this is my component form. How much is it moving horizontally? How much is it moving vertically? I don't want horizontal and vertical. I want the actual resultant force. So I want the magnitude of this. So we remember the magnitude of this is always your horizontal, once it's in component form, horizontal squared plus vertical squared. So then I can just go to my calculator, the square root of A squared plus B squared, because those numbers are already stored in there, gives me a final answer of 2,135.20 pounds, rounding to the nearest hundredth, so 2 decimal places. Okay, so here's where I would go. Let's take a second right now. I would take the video and pause it, draw a picture for number 2, and then what's force 1, what's force 2 in component form, add them together and at least come up with your numbers there. That's where I'm going to stop, and then I'm going to go back through how to find the resultant force. But take a second right now, pause the video here, try number 2 on your own, and then come back and see and check your answers. Okay, just coming back, I am going to go through how I set up my picture and then my horizontal and vertical components for both forces and then finish up this problem here for you. So the first one, we knew that 2 trucks were pulling out of the ditch. So there was one 2,000 pound force and the other one was a force of 2,300 pounds. And the angle between the 2 ropes is 43 degrees. Now, this question does ask for 2 things. It asks for the resultant force, which we know is the magnitude again, but then it asks for the direction angle from the 2,000 pound force. So since I want to be from the 2,000 pound force, this is the vector that I want to have as a 0 degrees. So from this one, where is this vector ending up, new vector, the resultant ending up coming from? And so since there's a 43 degree angle in between them, then 2,300 is going to end up with the 43 degrees. Okay, so as I add those two up from my component form, the horizontal component is 3,682.11, and the vertical component is going to be 1,568 point, I'm rounding here, 60. Again, we don't want to round, so make sure you're using the whole numbers in your calculator. Use that to help you store that as well. So I already have mine stored as A and B in my calculator. So the first thing that I'm going to do for the magnitude to get my resultant force is I'm going to take the square root of A squared plus B squared. So the square root of A squared plus B squared. Oops. Trying to get it so it can focus on the screen here a little bit better for you. So I have A and B already in there. And so then magnitude, squaring the horizontal, squaring the vertical, adding together, take the square root, is going to give me an answer of 4,002.31, and these are in pounds. All right, and then the last one is to find the direction angle. You did direction angle with Mr. Recht, and he always told you to do the tangent of your angle would be your vertical over your horizontal. So I'm just going to end up going inverse tangent of my vertical, which was saved as B, over my horizontal, which is going to be A. So inverse tangent of B over A. And doing it one nice step there gives me an answer of 23.07 degrees. And then this is where I liked having the pictures because we know this is 43 degrees. Oh, this angle from here to my new resultant is 23. And then it's got about 4,000 pounds on it. So it really should be pretty much double the length of whatever this one is, depending on how accurately you drew your picture. Okay, the last one, we're going to do this problem together right away. This is going to be three forces now. When we look at these three forces, we want the resultant force, so I want the magnitude, and the direction angle from the 57-pound force. Now, since this one is a horizontal line right away, a lot of people want to make this 0, but since I want the direction angle from the 57-pound force, this one is going to be my 0 degrees. And then there's 38 degrees in between these two, so this one is going to end up being 38. And then finally, I'm going to go all the way across from this being 0 all the way up here to my 72-pound force. This one's going to end up being 65. Now, we can't end up using the parallelogram law to draw what the resultant is going to look like, but even we can still use the same idea of adding up all of the vectors and finding the magnitude and finding the direction angle to help us with that. So I'm going to write my first force as 57 cosine 0, 57 sine 0. And then my second force is going to be my 103-pound force, cosine 38 degrees, and then 103 sine 38. And then my last vector is going to be 72 cosine of not 27. It's got to be the whole angle. How much far away is it from that 57? So cosine 65 and 72 sine of 65. So I'm just going to add these up real quick in my calculator. Making sure to save it as A. And then that one I got an answer of 168.59. And then I'm going to do the same thing for the next one, but it's going to be with sine. There's a lot of pieces here, so make sure you're typing them in correctly. Just double checking my work as well. And for this one, I got 128.67. And I'm going to save that one as B. All right, so now I have this one as A and this one as B. So we're going to do the same thing to find the resultant force and direction angle. Resultant force is the magnitude. So I'm going to do A squared plus B squared and take the square root of that. Gives me a magnitude of 212 pounds on my resultant force. That's how much there is there, how much it's pulling. And then the direction angle is the inverse tangent of my vertical over my horizontal. So inverse tangent of B over A in my case for the letters that I saved them at. And gives me an angle of 37.35 degrees. So I know it's going to be pulling, with all three of these pulling, this object is going to be pulling and have a resultant at 37. So it's just going to be just below here of where that 103 pounds is. It's pretty much going to be coming out horizontal again, since those were 38 degrees away. It's going to be a little bit less than that. And then 212 pounds. So if I would draw in the vector, it would be a little bit longer there as well. Okay. Please let us know if you have any questions, and work on the worksheet that goes over some other 2 3/4 problems. It's attached with all the rest of your information. Okay, thank you. See you later.